Imagine 3 closed doors. Behind one is a prize. Behind the other 2, nothing. You pick a door. Then the host, who knows where the prize is, opens a different door and shows you it is empty. Now you get a choice. Stay with your original door or switch to the only door still closed. Which is smarter? Most people say it does not matter. The math says otherwise. Most people guess 50-50. One door has the prize, one does not. So switching and staying feel equally likely. The math says your first pick only had a 1 in 3 chance. When a losing door is removed, that 2/3 probability does not vanish. It collapses onto the other closed door. Switching wins 2/3 of the time. Staying wins 1/3. This is a probability puzzle, not a betting pitch. You choose door A. The host always opens an empty door you did not pick, say door C. That action is not random. The host uses knowledge. Your initial choice still has a 1 in 3 chance of being right. The host's reveal transfers the remaining doubt to door B. The question is where the 2/3 went. Before anything opens, your door is right 1 time in 3. That fact does not change when a losing door disappears. Think of it this way. At the start, you are probably wrong. Probably means 2 times out of 3. When the host shows you one of those 2 losing doors, the whole probably wrong bundle lands on the single door you did not pick. Change the rules and the answer changes. If the host opened a door at random and happened to show empty, then yes, 50-50. But the classic puzzle assumes the host always reveals a goat, never the prize, and never opens your door. That constraint is the hidden ingredient. Conditional probability means new information reshapes old odds, but only when you know how the information was produced. Run the experiment mentally 100 times. Pick door A every time. Stay. You win about 33 games. Switch. You win about 67. The diagram is not philosophy. It is counting outcomes. When you always switch, you win whenever your first guess was wrong, and your first guess is wrong 2/3 of the time. Here is the picture that fixes intuition. At the start, either your door has the prize, 1/3, or it does not, 2/3. If it does not, switching must win, because only one door remains. So switching wins in exactly the cases where your first pick was wrong. That is 2/3. Staying only wins when you guessed right at the very beginning. Scale the puzzle to 2 doors to see the logic naked. One prize, you pick one, the host opens the other, it is empty. Switching always wins. In the 3-door game, your first pick is a wrong filter. The host's reveal does the same job as opening the only other loser, but leaves one consolidated alternative. Same structure, one extra door at the start. Here is the surprise. The puzzle feels unfair because brains treat the final 2 doors as a fresh coin flip. They are not fresh. Your first choice anchors a 1/3 claim. The host's action is a clue, not noise. Mathematicians call this updating beliefs with evidence. You already had a guess. The open door tells you where the remaining doubt lives. But I would have picked the other door anyway. Only one door stays closed. The math does not care about wording. Maybe the host is tricking me. In the standard puzzle, the host follows fixed rules. I still feel it is 50-50. Feeling is real. The count is still 67 versus 33 across many trials. Intuition catches up when you track where the 2/3 sits before the reveal. Recap. 3 doors, 1 prize. Your first pick is right 1/3 of the time. The host always opens a known empty door. That leaves 2/3 of the uncertainty on the other closed door. Switching wins 2/3. Staying wins 1/3. The puzzle is about conditional information, not luck, not superstition. See the diagram, and the answer stops fighting you. The Monty Hall puzzle tricks us because new information hides inside an old choice. Next time on Math Sketch, why negative numbers were once considered absurd, and how debts on a number line changed mathematics. Subscribe for weekly pattern hunts. This is Math Sketch.